So the function was sine x plus 0.6 cosine 2x. So the first derivative was cosine x plus minus minus 1.2 sine of 2x. And the second derivative is going to be negative sine x minus 2.4 cosine 2x. Is that right? Okay. So what you do here is you're going to replace cosine of 2x with the one that involves the sine squared. So this will end up being negative sine x minus 2.4, and getting my trig identity table out. Cosine of 2x is 1 minus 2 sine squared of x. And if you multiply that out, you get negative sine x minus 2.4 plus 4.8 sine squared x, or just rearranging it, 4.8 sine x minus sine x minus 2.4 equals 0. Then you have to use this sine squared. So then you have to use the quadratic formula. So you'd have that the sine of x equals minus negative 1 plus or minus the square root of negative 1 squared minus 4.8 negative 2.4, all divided by 2 times 4.8. So that's 1 plus or minus, get my calculator out. So that's 1 plus 4 times 4.8 times 2.4. So that's plus or minus the square root of 47.08 divided by 9.6. Square root of that is 6.86. So you get 1 plus or minus 6.86 divided by 9.6 plus 1 divided by 9.6 is 0.819, or negative 1 plus 1 minus 0.686 divided by 9.6, which is negative 0.610. So that's the sine of x. And then let's say this one, if you take the inverse sine of 0.819, put it in radians. I'll change that from yesterday. So if you do that, you get the inverse sine of 0.819, and you divide by pi, and so this is equal to 0.305 pi radians. Okay, so that's, hopefully I did that right. Where's my solution, since I'm doing it kind of quickly? Where's my, oh, here it is. Yeah, okay, so that's the first one, 0.305 pi. Your next one would be the sign is positive in the first and second quadrant, so your second quadrant solution would be pi plus 0.305 pi, which would be 1.305 pi. That's where you get that one from, except that's not what I have. What did I do around here? I got 2.09 pi. Okay, what did I do? Oh, I got to subtract pi. pi minus that. Sorry, it's the second quadrant. So the second quadrant solution is you take pi minus 0.305 pi minus 1 equals 0.695. That's the second one. And you do the same thing here, except this is going to be in the third and fourth quadrant because it's negative. So that's how you get it. So yeah, it's not easy to get all that stuff, but anyway, so go ahead and turn them in. See how far you got. I just don't want anybody working on it in class. What I will do is I'm going to just see who finished it completely, and then I'm going to hand it back, and I'll let you fix. You can, now that I've shown you how to do the second part.
So how would you get quadrant 3?
You would add, you take the inverse sine of 0.610, and then you convert that. So let me show you. So what you do is to get the third quadrant solution, you use the other number. So you take the inverse sine of 0.610. So if you take the inverse sine of 0.610, inverse sine 0.610, and then divide by pi, you would get 0.209 pi. So your third quadrant solution would be pi plus 0.209 pi, which would be 1.209 pi. And your fourth quadrant solution would be 2 pi minus 0.209 pi, which would be the last one, which is 1.791 pi. So that's how you get the other ones. Anyway, somebody's already turned them in. But what I'll do is I'll take them in now, and then I will bring them to study session once I've decided who's completely got them. I just want to see who's done them all here. Okay, thank you. I just want to see who actually got the answer initially. But if I hand them back to you, now that I've shown you how to do it, you can go ahead and clean it up. Is there any left? Any more? So I'll let you finish it up later. I'm just curious who the stars are here. Okay. I did that kind of fast because I didn't want to give you enough time to write it all down. So does anybody have any questions about what I did now that I have your papers? Yes.
So when you were going through the quadrant, you're taking the reference angle which we found was 0.305 radians. You're taking that number and either subtracting pi or depending on.
Yeah, depending on what quadrant you're in. So because the sign is positive in the first and second quadrants, then the first quadrant solution is just the reference angle. And the second quadrant solution is pi minus the reference angle. Because remember, the reference angle is the angle closest to either the positive x-axis or the negative x-axis. So now that you guys have had practice doing reference angles, let's review what it is. So, in the first quadrant, the reference angle is this angle, which is your first quadrant solution. So that would be 0.305 pi. Your second quadrant solution is going to have the same angle between the nearest axis and the angle. So this angle here, the total angle is pi. So if you take pi, subtract the reference angle, that gives you the angle. So that's the second quadrant solution, which is 0.695 pi. And then the third part here, this one here is negative. The sign is negative. So when you take the inverse sine of this number, you get the reference angle, which is in the first quadrant. So that's your reference angle. But your third quadrant solution is going to be the same distance angle-wise from the nearest x-axis. So you take pi and you add the reference angle. So that's how you get that. And your fourth quadrant solution, again, has the same reference angle as this solution when you take the absolute value. And so you take 2 pi minus the reference angle. That gives you the total angle that you come up with. So that's how they work. Anyway, I will, like I said, I'll let you turn it in. And well, I got to figure out where I keep losing my papers. What did I do? Where did they go? Okay, somebody stole my papers. Where are they? Oh, there they are. Somebody didn't. Oh, Evan. Okay, Evan did put his name on it. Okay, so like I said, I'll hand these back, let you clean them up in study session. So we were finishing up. Done is we had taken the first and second derivatives of the rational function. We'd set the numerator is equal to 0, found the values of x where the numerator went to 0. Those gave us the critical numbers, which turned out there's only one critical number. Well, actually, there were three critical numbers. One where the function was 0, and 2 where the function did not exist. The second derivative never went to 0, so there were no possible points of inflection at 0, but there were 2 cases where the function does not exist. And we could create the table, and I'm just going to show you the table down here. It's in your book, so let's put it here. Okay. So you could create the table by using those 3 numbers to define the intervals. So they are, and remember this is the new table for curve sketching, which you include the value of the function, the sign of the second derivative, first and second derivatives, and then you make comments about what's going on. So we include the critical numbers as well as the possible points of inflection. So at the points where the function is undefined, the derivative and the second derivative are undefined, those are your vertical asymptotes. At x equals 0, you find the value of the function, which was 9 halves. So that's where you're either going to have a minimum or maximum. If there is a change from decreasing to increasing, which there is, or increasing to decreasing. So this is a critical number. And because it's concave up, it's a relative minimum. You could pick values of x in these intervals to evaluate the sign of the first and second derivative. So I'd pick -1 here, I'd pick +1, I'd pick +3, maybe -3. So the numbers, and all you're doing is looking for the sign of the first and second derivatives. So when you do that, you find out that we're decreasing. We have a change from decreasing to increasing, which means it's a relative minimum. We have another vertical asymptote. This is where it's increasing. And the second derivative says it's concave down, vertical asymptote, concave up, concave down. So what we can do is we can use all that information plus the things that we hadn't done yet. So let's go back to do that. We said, how do we find the other stuff? Well, the x-intercepts, what you do is you take the original function here and you factor the numerator. So x squared minus 9 is x plus 3 times x minus 3. So in the original function, the numerator goes to 0 at these 2 values of x, 3 and -3. So those are your x-intercepts. Your y-intercept, you'd set x equal to 0. So that just leaves 2 times -9 over -4. which would be positive 9/2. So that's how to get the y-intercept. The vertical asymptotes are where the original function is undefined. So if you factor the denominator, you'll see that at x equals -2 and at x equals 2, that the denominator goes to 0, and therefore you have vertical asymptotes there. Your horizontal asymptote, it's the same order as far as the order of the polynomial in the numerator and the denominator. So the rule says from section 5, you use the ratio of leading coefficients, which would be 2 divided by 1, which is 2. So that's why that's the horizontal asymptote. So that's how you get all these answers. Set the numerator of the original function equal to 0. Set x equal to 0 in the original function. Factor the denominator. Find out values of x where the denominator is 0. Use the rules for horizontal asymptotes. This came from the fact that the first derivative is 0 only when x equals 0. And again, you just look at the numerator. The domain is all real numbers except for where it's undefined. There are no possible points of inflection because there's no places where the second derivative goes to 0. Okay, so let's plot the function now, given all this information. And we could have actually done a pretty decent plot even without calculus as far as the rational functions. But it does give us some extra insight into what's going on. So what you do is you, let's just go down the list of things that they've given us. So you've got the x-intercept, so and we have to set the axis. And I think just going from -10 to +10 is sufficient in this case. So if you plot this is a point, that's the x-intercept. This is the x-intercept. We have a y-intercept at 9/2, which would be 4.5. So that's 1, 2, 3, 4.5. So that's your y-intercept. You have vertical asymptotes at x equals -2, +2. That we have a horizontal asymptote y equals 2, so I'm going to draw a horizontal line outside of these things here. So that's y equals 2, y equals 2. And that's about it. Oh, we have a critical number at x equals 0. We found out the value of that was 9. So that's actually right here. So there's a critical number right here. So before you had calculus, we would say, which way does this function approach the horizontal asymptote? Well, it has to approach it from the bottom, because if it approached from the top, it would have to cross here, and that's not going to happen. So you're not going to have that happen. The only way it could cross here is you'd have to have some kind of maximum, and then it would go. So there's no maximum there. So it has to come from the bottom side. So it would come along and go like that. Let's draw that in and see if it agrees with everything that we've written down here. So so it comes up from the vertical asymptote, goes through this point, goes over like that. So let's confirm. It says it is an increasing function, which it is if you go from left to right, and it's concave down, which it is. If I did it the other way, it would be decreasing concave up. This is increasing concave down. So that's what calculus tells us. Pre-calculus just says it has to go this way because it has to stay in this little quadrant that I've set up. Okay. Then we have vertical asymptote. Then it says we have an increasing function that's concave upward in the next interval. So to be an increasing function, it has to go like that, and it is concave up, so that agrees. We have our minimum here. The next part's decreasing, and it's concave up also, so that agrees with the first and second derivative. And likewise, this one has to come from underneath the horizontal asymptote through this point and then down to there. Again, it's a decreasing function, and it's concave down because the curve is downward. So everything we filled out on the table confirms what we would have guessed anyway beforehand. So it doesn't, calculus in this case doesn't help us quite as much as just things we could have also gleaned from pre-calculus. So I'm not going to go through all the details of this. I'm just going to summarize how it all works out, and you can. So it's another rational function. The difference with this rational function is it's not. Notice the order of the numerator is greater than the order of the denominator, so it's not going to have a horizontal asymptote. It's going to have a slant asymptote. And that's what this little extra calculation is. So the slant asymptote is y equals x. If you factor the numerator, which I don't know, I guess you could. Actually, no. You'll find out there are no. If you try to factor the numerator, you'll find out there are no real factors because it says here x-intercepts are none. How would we know that? Let me just put an extra page here. So if you tried to, if you tried to look at the numerator here and said, what values of x does this go to 0? Well, you could use completing the square. So if you did that, you'd have, you'd move this to the other side. You take -2, divide by 2, square it, which is going to be equal to 1. So this is plus 1. And we add 1 over here. So this is x plus 1 squared. And this is -3. So when you try to take the square root of this, you'll see you have the square root of a negative number, and therefore there are no real solutions. That's why the x-intercepts are none. Then you'd use the quotient rule to come up with the first derivative, and then use the quotient rule again to come up with the second derivative. So in terms of when does the first derivative equal 0, well, you look at the numerator, and you see at x equals 0 and x equals 4 that you have the case where the first derivative equals 0, and that's why the critical numbers are 0 and 4, because those are the numbers that make the numerator of the first derivative go to 0. The first derivative is undefined at x equals 2 because the function's undefined at x equals 2. So the vertical asymptote is where the denominator goes to 0. That's at x equals 2, so that's how to get that. There's no horizontal asymptote because this is squared and this is the first power, but there is a slant asymptote. The end behavior, as you go to positive infinity, y goes to positive infinity. You can see that from the slant asymptote. The second derivative is never 0 because the numerator is 8, which is always 8. So that's why there are no possible points of inflection. So when you make up your table, you've got, you start from negative infinity, you go to 0, which is one of the critical numbers. Then you go between 0 and 2, which is the vertical asymptote. Then you go from 2 to 4. 4 is the other critical number. And then you go from 4 to infinity. You evaluate the function at the critical numbers. So you plug in x equals 0, you get -2, and you plug x equals 4, and you get 6. First derivative is 0 here from looking at the critical numbers. First derivative is undefined. There are no cases where the second derivative is 0. And then you can plug numbers in these intervals. Pick a value of x, evaluate the sign of the first and second derivatives, and you can fill out the table as such, and then you can make comments. It's increasing, concave down, decreasing. So here there's so because this is concave down, it's going to be a maximum. Also because we go from increasing to decreasing. So both the first derivative test and the second derivative test tell us that this is a maximum. Likewise, over here, the first derivative test says we're going decreasing to increasing, which is a valley, so that's a minimum, or because it's concave down, which is also, that's the second derivative test. So both the first derivative test and the second derivative test tells this is a relative minimum. We did a polynomial already. Just seeing what I got here. Okay, before I assign the homework, we're going to go through another problem. It's another rational function problem. So we're going to populate our table at some point. So we need to take the first derivative using the quotient rule, and then we'll use the quotient rule again to find the second derivative. By the way, there's a 90% chance that the next test in this class will be not next Monday, but the following Monday. And I haven't told Mr. Graham yet, but that's our fall trip to New York. So you're gonna have tests. Mr. Watkins is going to proctor the test that day, but I won't be here. And then once you finish, you'll have the normal hour and 50 minutes, and then there'll be a take-home part that you can work on after that, which will be one of these kinds of problems. Okay, so you won't have a curve sketching problem on the test, but you will have one for a take-home part of the test. The rest of the test will be everything except section 6. So it'll be first, second derivative tests, critical numbers, optimization, which we haven't talked about yet, which we're going to spend a lot of time on, and horizontal asymptotes. Most people do okay on this test, fairly straightforward. Mostly because the stuff that you have tests on is polynomials, and the derivatives are easy to take for those kinds of things. But just so you have that on your schedule. And I think next Friday will be the next physics test for chapters 5 and 6. I will be here for that, but I'm leaving right after class. Actually, yeah, I keep forgetting you guys are not, your Monday's going to be a problem for you guys in terms of having extra time because you have biology. So I'm not sure what I'm going to do about that. So, but we'll still have the test. I'll figure out some equitable solution. Okay, so actually I'm going to call this h of x so let's just work through this. F of x equals 2x, g of x equals x squared minus 1. So f prime of x is 2, and g prime of x is 2x. So the quotient rule says that the derivative of a quotient is f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. So if we multiply out the numerator, you get 2x squared minus 2 minus 4x squared, all divided by x squared minus 1 squared, which is negative 2x squared minus 2 divided by x squared minus 1 squared. Just double check here. Which you could factor out the -2. So you get -2 times x squared minus 1 divided by x squared minus 1 squared. Something's fishy. Hold on just a second. The reason something's bothering me here is because, oh, it's +1. There we go. That makes more sense. So when I factor out -2, I'll get -2 x squared plus 1 over x squared minus 1. So let's think about what values of x does the numerator go to 0? Well, almost. Square root of -1. So there are no values. Yeah. So because you've got x squared plus something. If it was negative, then you'd get the square root of whatever this number is. But here, so there are no values of x where the first derivative goes to 0. So we can write that no values of x where f h prime of x equals 0. Okay, now we do the second derivative, so let's add a page. So we take, so if, I'm going to call it m of x, just because it's just because it will allow me to I'm going to call the top part f of x equals -2 times x squared plus 1. G of x is x squared minus 1 squared. So f prime of x equals -2x. And g prime of x, I'm going to use the chain rule and I'm going to leave it factored. So you're going to have 2 times x squared minus 1. Reduce, so you take the exponent, reduce the exponent by 1, multiply by the derivative inside the parenthesis. So g prime of x is going to be 4x times x squared minus 1. So I'll call this m prime of x is going to be equal to -2x f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. Yep. Thank you. So that's -4x. So this needs to be -4. Okay, make sure I didn't mess anything else up. -4 times that. Okay, so you can factor out one of these x squared minus 1s. You're going to have 4 of them here. I've got 2 of them there and 1 of them there. So let's just do that simplification. So you're going to have -4x times x squared minus 1. So I'm going to take one of those. Negative times a negative is a positive, so it's going to be positive. 2 times 4 is 8. And I've got an x. So negative times a negative is positive. 2 times 4 is 8x. And then I get to cancel this one out. So then I'm left with x squared plus 1, all divided by x squared minus 1 cubed. So again, I've got 4 of x squared minus 1s. X squared minus 1 to the 4th power. I'm going to take one of those, so that gets reduced by 1. This one gets canceled out completely, and I'm just left with this times that times that times that. Then you multiply it out, so you get negative 4x cubed plus 4x plus 8x cubed plus 8x, all divided by x squared minus 1 cubed. So we end up with 4. 8 minus 4 is 4. Here. So you get 4x cubed plus 12x, all divided by x squared minus 1 cubed. And you can factor out an 4x, so you get 4x times x squared plus 3 divided by x squared minus 1 cubed. So that's the second derivative. That's h double prime of x. Again, there are no roots to this because it's plus. So the only value of x where the second derivative is 0 is when x equals 0. And it's undefined at plus or minus 1, the same where the original function was undefined. So what we can say from that, looking at the second derivative, setting that equal to 0, which means setting the numerator equal to 0. So for what values of x does this equal 0? Well, the answer is when x equals 0. So that's a possible point of inflection. So we've got two vertical asymptotes back here to the original function. We've got two vertical asymptotes which are going to help us define the intervals at plus or minus 1, and we also have a possible point of inflection at 0. So that's how we're going to break up the interval, the original interval, which goes from negative infinity to positive infinity. So the intervals are from negative x infinity to negative 1. Then x equals negative 1. Then from negative 1 to 0. Then x equals 0. Then from 0 to positive 1. And then x equals positive 1. And then from 1 to positive infinity. So remember, this is undefined. The first derivative, the function, the first derivative, and the second derivative are undefined at x equals negative 1 and x equals positive 1 because those are vertical asymptotes. And then we have the second derivative is 0 here. And if you evaluate the function, evaluate the second derivative at 0, what do you get? You get 0 because you have 4 times 0, so 0 times anything is 0. So the value of the function is 0. So we have 1 point. And then you have to look at the sign of the derivatives at these values of x. So you have to pick some value of x. So if I picked it, let's say at x equals negative 2, the first derivative, what's the sign of that? And what's the sign of the second derivative? Well, let's start with the second derivative. At x equals negative 2, this is positive, and this is greater than that. So all of these are going to be positive, but this is negative. So ultimately, that gives you a negative answer because of that. Okay, x squared is positive. This is positive, but it's a positive number greater than 1. So when this number will be positive, and a positive number cubed is positive. So that's the only thing that derives the sign of the second derivative. And you can so let me just put that in there. So this is negative. And for the same reasoning, this one's positive. If I plug in positive 2 in this interval, everything's positive, so I don't have to worry about anything. Okay. Now go to the first derivative. First derivative was, where's the first derivative? There. So again, this is positive always. This is positive when x is either greater than or positive 1 or less than negative 1. So this thing, the first derivative, is going to be negative for both positive 2 and negative 2. So we're going to go here, and those become, so these are negative. And then you evaluate some number between 0 and negative 1. So what happens here is between 0 and negative 1, this actually, a negative 1, this becomes negative 0.5, say. If you put negative 0.5 in, this number, this quantity is going to be smaller than that. So this thing's going to be negative, and a negative number cubed is negative. So this is negative because it's negative 1/2. So this ends up being positive. And if you have positive 1/2, this whole thing is positive, and the whole numerator is positive, but this part's negative because you have 1/2 squared, which is a quarter. Quarter minus 1 is negative 3/4. So this is going to be negative. So this one turns out to be negative. And then if you go back to the first derivative, this quantity is squared all the time. This is always positive. So these are both positive. So this is always negative. This first derivative is always negative. So they're filled in everything now. So let's see if we can draw this thing. Let me see if I got a piece of graph paper. There you go. So we've got all this stuff filled in. We didn't come up with the horizontal asymptote. The horizontal asymptote, we go back to the original function. And if you look at the original function, the order of the numerator is smaller than the order of the denominator, so that means this goes to 0 when x goes to infinity. So using the rules that we know that the horizontal asymptote is y equals 0, and that's why you see there. Okay. So we have one point to plot, which is that point. That's where we have a point of inflection, but not a minimum or maximum because it's increasing or decreasing. So because this thing's decreasing the entire time, so if I were to start this function above the x-axis and went this way, it would be an increasing function, which obviously is wrong. So it has to start out here, and it has to then go down like this to the vertical asymptote. Now the next part, and it's concave down. Now the second part here, it's still decreasing, so I have to start up here. I come down through this point. I have a point of inflection where it changes from concave up to concave down, but it's still decreasing until I get to the bottom of the vertical asymptote. Then I come to the top of the vertical asymptote, and it's still decreasing, and it's concave up, and it approaches the horizontal asymptote. So that's what the function looks like. So again, what I did was I said I'm starting here from the left. It has to be decreasing. So if I started here and I decreased, I'd have an x-intercept, which I don't. So I have to start below the curve. Also, by decreasing all the way like this to the asymptote, I'm having a concave down situation, which agrees with what I have as a second derivative in that first row. Then I have my vertical asymptote. Now if I came up this way, I'd be an increasing function, so I can't do that. I have to come from the other direction. So I'm decreasing. There's a little bit of curvature, which is in that direction. I come through this point, which is a point of inflection, where the second derivative changes from concave up to concave down. And I'm continuing to decrease all the way as I approach this vertical asymptote. Then I have to come up on the other side. Again, I can't come from this direction because then I'd be increasing. So I have to start up at the top again. So I come down and I approach the horizontal asymptote from the top so that I have the curvature in the correct direction. Okay, so I'm going to sign these for you to do because the only way that you can do it is by practicing. Luckily, because they take so long, I'm not assigning a huge amount of problems. So there's 1 through 4 are probably just looking at graphs, and then 12, 17, 25, and 30 are actual functions. But, you know, and they are complicated, okay, but it's because this is the culmination of stuff you've learned for years and years and years and years and years and years and years. So it's a lot of stuff put together, but it's stuff all that you have had at least you've had multiple times, except for the derivative stuff. So we're going to move on to the next section now. This is going through, I know that you have a hard time paying attention because they're so long. That's why you need to do them at home instead of me doing them in class. As I said, you will have a take-home portion of a test, which will do just one problem. It could take you the whole period if you did this as a test problem. So we can't do that. Now, the more practical and useful application of derivatives is this next section. So these are called optimization problems. Again, that's why business majors take this class ultimately. They don't really need to know integrals. So if you took a business calculus class, you probably would never get to integrals. You just do deal with derivatives. With this application as your sole goal. But anyway. So the basic idea here is you have to, if you can mathematically model some situation, whether it's business or whether it's manufacturing or construction or anything that you can put an equation to, something is a function of something else. If you can find where the first derivative is equal to 0, you're at a possible maximum or minimum. If you're trying to minimize area, minimize cost, maximize something. So the calculus part of the optimization problem is usually not that difficult. The difficult part of optimization is coming up with the equations that you need to apply, kind of like related rates. So you're probably dreading it from that perspective. But anyway, we'll do our best here. Now this is on page 219, so I'm not going to ask you to write it down. You can write it down if you want to write it down for your cheat sheet at some point. You can. But we're going to go through all these steps in all the problems. So the first thing is you identify all given quantities and quantities to be determined. It sounds like a physics problem. In some ways it is. It's a word problem. And if possible, make a sketch. Sometimes drawing a picture is very helpful. And you typically have, most optimization problems have what's called a primary equation, and that involves the variable that you're trying to minimize or maximize. So if you're trying to minimize area of something, or let's say maximize surface area given a volume, the quantity you're trying to maximize is the surface area. And that can be a function of radius. It's usually a function of, the dimensions of the circle or the sphere. But typically there's also a secondary equation, and we call that a constraint. So for a particular, an equation for an area applies in general, but there may be specific restrictions on the dimensions, the sizes of the different dimensions. You may say it can't be bigger than this, or the sum of this plus the sum of that has to equal something. So typically you have to use this secondary equation to reduce the primary equation to having only one independent variable, because we are studying calculus of one variable. If you take Calc 3, you'll do calculus of multiple variables, but right now we're just doing one variable. So usually y is a function of x, or something like that. We did that in related rates when we were doing the calculation of the increase in height of the pyramid, or the cone of gravel. We had the height and the radius had some kind of relationship, and we had to substitute that in to get it either in terms of just radius or in terms of height, because we couldn't do both of them. Same kind of thing here. You typically take your secondary equation, use substitution into your primary equation to get it in terms of just one variable. Which again, we do that in physics, that's algebra. In this case, we're using it to come up with an equation and then take the derivative. So once you have substituted the secondary equation to the primary equation so that it's a function of only one variable, then you take the derivative and you also limit your domain to feasible solutions. So if you could have a mathematical expression that would give you a negative area, but you know that area cannot be negative. So you would use you'd say my number has to be between 0 and 100, because it can't be less than 0 because physically you can't have negative lengths, and it can't be greater than 100 because of some other constraint. So sometimes you can have two solutions, but only one is reasonable. So you do that by looking at what is the feasible domain. And then finally, you use derivatives. You take the first derivative and determine if there are any points that have 0, find any critical numbers, and then you can either use the first derivative test or the second derivative test to determine whether they're maximums or minimums. Like I said, the hard part is figuring out what the equations are, both the primary equation and the secondary equation. So we're going to go through a lot of problems. The first problem is actually just a number problem. First couple of homework problems are that way too. So it says the product of two numbers is 192, and the sum of the first plus 3 times the second is a minimum. So there's two equations involved here. There's an equation associated with this statement, and there's an equation associated with this statement. The second equation, because they're saying it explicitly, is the one that we're trying to determine minimums or maximums. So the first thing you do is you identify all given quantities and all quantities to be determined. If possible, make a sketch. In this case, we don't make a sketch because they're just numbers. But we're just going to define. We pick the letters to use as the variables. So we're going to say there's two numbers, and the first number is x, and the second number is y. And the sum is s. So this is the sum from this equation. And really, we have one more, which, well, we don't really need to. We could say P is the product, but we don't actually have to do that. Okay, so the second one is come up with your equations. So the primary equation is the one we're trying to either minimize or maximize. So it says the sum of the first number, which is x, plus 3 times the second, is minimized. So the sum is just the first plus 3 times the second. That's my primary equation. But you'll notice that there are two variables, x and y. So we need to use this secondary equation, this constraint, so that we can rewrite this in terms of just one variable, either in terms of x or in terms of y. It doesn't matter which one we do. So I'm just going to write what the secondary equation is, and then we'll start on this on Thursday. But the secondary equation is going to be x times y equals 192. The product of the two numbers, which is what that is 192. So what we're going to do is we're going to solve either for x or y, substitute in here to make this entire right-hand side in terms of one variable, and then we'll take the derivative with respect to x or y, depending upon which substitution we choose, and use the stuff we learned in calculus to figure out what are the x and y values that satisfy these restrictions. Okay, so that's it for today.